Hello there. So far, we have learned and applied the special trig limits, but not yet trigonometric limits in general. So the question is, how do we obtain these limits of trigonometric functions in general? So that is what we'll be finding out in this video. To answer this, let's first recall some previous things that we know or we have learned in the past. So first, take note that if f is continuous at a point, say A, it follows that the limit of f of x as x approaches A is equal to f evaluated at A. So this is just by the definition of continuity at a point. Next, if a function f is continuous at the limit of another function, say g, at the point A, then it follows that by a theorem in the past, we know that the limit of f of g of x as x approaches A is equal to f of the limit of g of x as x approaches A. Basically, if this function f, this function outside, is continuous at the limit of this function inside at the point E, then we can move this function f outside of this limit, out here. So this is something that we know by the composite limits, the theorem that we presented in the past regarding the composition of limits. So I hope you recall that one. For this third one, this isn't really a recall, but this is something that we should take note. Take note that trigonometric functions are actually continuous on their respective domains. What are these domains? That is what we'll be recalling. So we have here the domain of trig functions. So by this time, you should have an understanding of how or what these domains are. So to present it or to recall it, take note that for the sine function, sine of x, its domain is given by all real numbers. Next, for the cosine x, its domain is similar, just all real numbers. For the tangent of x, now this one is different. Its domain is given by all real numbers minus the 2k plus 1 times pi over 2, or the odd multiple of pi over 2. So take note of that one. For the cotangent of x, this one is given by, its domain rather is given by all real numbers minus, so just to reiterate, this one out here represents minus or set minus, so minus the integer multiples of pi. And then for the next one is the tangent cotangent, that would be the secant function. Its domain is given by all real numbers minus, again, the odd multiples of pi over 2. And lastly, the cosecant of x, its domain is given by all real numbers minus, again, the integer multiples of pi. So these are the things that we need to take note and recall in order to obtain the limits of trigonometric functions in general. So basically, we'll be using the concept of continuity in obtaining these limits. So without further ado, let's have these examples. First, we have the limit as x approaches pi of tangent of x. Second, we have the limit as x approaches negative 2 of cosine of x squared minus 4. And third, we have the limit as x approaches positive infinity of sine of 1 over x. So before we solve each of these examples, feel free to pause the video so that you may try this first on your own. Okay, good. So let us start. For the first example, to solve this, take note that pi out here is actually part of the domain of tangent of x. So it's part of the domain of tangent of x, since if we recall earlier, the domain of tangent of x, this represents all real numbers minus the, I think this is the odd multiples of pi over 2. Clearly, this isn't a odd multiple of pi over 2, so it's part of this domain. So that means that by continuity at a point, take note that the pi out here, we just simply plug that in our function, in this case tangent of x. So we'll have your tangent of pi, and if you know the answer for this one, you can immediately conclude with that one. But if you don't know, take note that tangent of pi can be expressed as sine pi over cosine of pi. And this one, we know that sine pi is equal to sine of pi is equal to 0 there, and cosine of pi is equal to -1. So we'll have here 0 over -1, or simply just 0. That answers the first limit. For the next one, this one out here, we will be applying the idea of composite limits. So observe that the cosine function, we know that this one is continuous everywhere. Since its domain is all real numbers, it follows that, again, trigonometric functions are continuous at their respective domains. So cosine is also continuous at all real numbers. This means that by the composite limit theorem, or the second bullet point in our recall, the cosine out here can be moved out of the limit. This means that we can solve first for the limit inside, and fortunately, x squared minus 4 is just a polynomial. So we can simply plug in -2 into the function. That would give us -2 squared minus 4, and this is just equal to 4 minus 4 there, and we know that 4 minus 4 is just equal to 0. So we have here cosine of 0, or just simply that would be 1 there. That answers the second limit. For the final one, so I hope you got those two examples correctly. For this final one, we just simply apply the idea that we used in the second example. So take note that the sine out here is continuous everywhere, since again sine functions are or has a domain of all real numbers, so it's also continuous at all real numbers or everywhere. So that means, again, by the composite limits theorem, the sine function out here can be moved out of the limit, and we can first solve for the limit inside instead. Solving for this limit, this is just using the concept of infinite limits. So we know that 1 over infinity, or a value of 1 over infinity, or a value approaching 1 over infinity, is approaching 0. So we'll have here sine of 0, or simply just 0. That answers the last example. So I hope you got these examples correctly. If the presentation of the solution is quite quick, you may comment it down below and I'll try to slow down next time. But yeah, I think the process out here is very straightforward and much easier compared to the special trig limits. But for these exercises, so we have here first the limit as x approaches 0 of cosine of pi sine x over x, and the limit as x approaches 0 of tangent of 1 minus cosine x over x. You'll be needing the concept or the idea that we had in this video, as well as the special trig limit. Since observe that these out here, sine x over x and 1 minus cosine x over x is parallel to the special trig limits. So it's your goal to make these special trig limits appear out here and solve for these problems. Yeah, so yeah, I hope you enjoyed and learned a lot from this one. So yeah, if you have any questions, suggestions, and recommendations, you may comment it down below and I'll try my best to respond and answer those questions that you have. So yeah, that is it. And yeah, again, apologies since I wasn't able to post any videos last week since I got quite busy, but yeah, I'll try my best to continue posting these videos and to be able to help you in your respective studies. So yeah, that's it, and that's all for this video.